So this section is what we like to call a qualitative section, meaning that it doesn't have a numerical answer. Its answers are going to be descriptions and reasons. Let's look down at the bottom of the next set of graphs. You've got 4 questions that call to attention these 6 graphs. And notice how these 6 graphs don't have labels on their x-axis and y-axis. It's going to be up to you to read the question to see what the labels make sense. Let's go to number 1. During the first few years, the number of deer on the island increased by a steady percentage. Okay, I'm going to draw a little axis here, and we're just going to talk about the number of deer on the island increasing. Maybe this is the number of deer, and this is time. That's one possibility, because it talks about during the first few years. As food became plentiful, the growth rate... Ooh, there's a word rate there. I'm going to pause again. Another word for rate is going to be slope, because slope is defined as a change in y over a change in x, and that is a ratio. If you take the first 3 letters of the word ratio, you have a rate. It's actually a rate of change. How many deer are there relative to the amount of time? Now the number of births and deaths is about the same. So if the number of births and deaths is about the same, that's going to be no change. So what we'd expect from a graph like this is the first few years, the number of deer on the island increased slowly. So you're going to have kind of a gradual slow into the treadmill. You're going to have kind of something being a little bit slow. And then as food became plentiful, the growth rate increased, and the slope rate shot up and increased. So if you look at the way I've drawn this little sketch here, you have a section of that line that's a little bit less of a slope. Something like this. And then I have a section that's an increased slope, a steeper hill, like that. Now the number of deaths and births is about the same, so it's going to kind of level off a little bit. So we're going to look for a graph that's going to match that. Okay, let's go down to our options and look at what's going on. I have 2 candidates. I have graph 1 and I have graph 5. That looks something like that. Now, birth rates aren't going to change by sudden drastic changes here and here. There's actually a word for that called a cusp. They're not going to change by cusps. They're going to change more like this, where you have gradual increases and decreases. So I would argue that graph number 5 is probably our best bet to match this situation. Let's look at number 2. In the northern hemisphere, the amount of daylight increases slowly from January to February. Okay, right away I can kind of tell what kind of graph this is going to be. Similar to before, we have the amount of time, and then I have daylight. That says daylight. Go with it. The amount of daylight increases slowly from January through February. So we're increasing faster until mid-May. Then again slowly until the maximum in June. Then it decreases slowly through July. So it's decreasing slowly, then faster, then slowly again. So we got this like slow, fast, slow, then decrease, slow, fast, slow. Well, that looks like a kind of bell curve, and if I look at my options here, that's going to graph, that matches number 3 pretty well. Now, why number 3 and not number 2? Number 2 comes down to the x-axis, where the amount of daylight is actually zilch, or 0. We don't live in Alaska. We do have daylight all year round. This isn't like the 30 days of night thing. So what's going on here is that this type of graph in number 3 would actually then kind of continue and form a pattern like that, which should make sense because, you know, as the years go on, the pattern continues. So our best graph is graph number 3. Then, question 3. If you have a fixed amount of fencing, the width of your rectangular garden determines its area. If the width is very short, the garden won't have much area. That second sentence should tell you what your graph is going to look like. Meaning, if the width is very short, then the garden won't have much area. Less width, less area. So if I have less width, less area, I'm going to have something down here. As I increase the width, I'm going to have a lot of area. So you increase the width, the area increases. The area increases more slowly until it reaches a maximum. As the width continues to increase, so as you get more to the right, the area becomes smaller more quickly until it is 0. So we're actually going to hit the axis here. Well, we should also know that the width is 0, the area is 0. So we should hit the axis here. If width is 0, area is 0. That means 0 is 0 is an ordered pair. That means you have the origin as an ordered pair. So going back down here, the one that matches that is the graph number 2 that we didn't pick last time. Finally, your cup of tea is very hot. The difference between the tea temperature and the room temperature decreases quickly as first as the tea starts to cool to room temperature. But when the two temperatures are close together, the cooling rate slows down. So we have tea temp and room temp. Tea temperature and room temperature. So the tea temperature, the difference between the tea temperature and room temperature decreases quickly at first. So maybe instead of as I look at this, it's the difference between the tea temperature and the room temperature. If this one would be room temperature, this could be the difference. This actually creates a different effect here. If we have a big difference, we start off with a big difference, and maybe this isn't tea temperature, maybe this is time. And the difference is going to start off pretty high, then eventually it's just going to level and flatline. It actually takes a long time for the tea to finally reach room temperature. That is sort of like a getting close to, but never reaching. Now, in reality, it will reach room temperature, but it would just, mathematically, it would be very, very, very close to, but never touch it. So if this is like room temperature here, with this dotted line, this curve is going to become infinitely close to it, almost never touch it. So if I look at the graph that matches that, that's just like the graph number 4. Where this would be our room temperature here. The graph starts plummeting. Remember, this axis on the left represented the difference, and the base represented time. Now look at how many times that your x-axis represented time. It's actually very common to put the time factor on the x-axis. This would be graph number 4. Okay, moving on to the next page. You can have questions like this. The graphs show the distance of a person from a fixed point for a 4-second interval. You have time and you have distance. Answer both questions for each graph. A, is the person moving toward or away from the point? So one thing we're going to look to for A is as time increases, as time kind of goes on, the distance does what? Well, the distance actually increases. Time increases, distance increases. As more time passes, my distance from the point increases. That is moving away. Then B is the person speeding up, slowing down, and moving at a constant speed. Well, if you can see, we have a steeper slope, and that's going to affect things. If I have a steep slope, and my distance is increasing faster than my time, or faster relative to my time, that is a speeding up. Let's look at number 2, or the second graph. These aren't numbered. As my time increases, my distance decreases. If distance is decreasing, we're moving toward. Speeding up or slowing down, it's kind of flattish here, but as it's getting more steep, that is a speeding up. Not speeding, but speeding. Okay. Next, as time increases, distance increases. That's away. My distance is getting further away. My distance is increasing. Person speeding up, slowing down, or moving at a constant speed. Well, look at this. The slope is unchanged. That's different from the previous 2 graphs where your slope is actually changing. Here your slope is there, and my slope, here, let me kind of draw these. These are called tangent lines, by the way. There's a slope, there's a slope, there's a slope, there's a slope, there's a slope. My slope is changing. I try to do that at every point, it's just going to continue to be that line. That is always the slope. So, constant speed. Constant speed means constant rate, means rate is unchanging, means ratio is unchanging, means slope is unchanging. Okay, next one. As time increases, distance decreases. That is torn. In this one, I'm starting off with a very steep drop, but then I'm eventually flatlining or kind of getting less and less and less steep of a slope. That is slowing down. As slowing. I know. If you can't hear that, I'm sure Gino will make fun of me. This one, as time increases, distance decreases. That's also toward. Look at all the toward ones and what they have in common, by the way. If I look at the second one, the fourth one, and the fifth one, all of the toward ones have an effect of, well, you can see it for yourself. They're starting off at a higher point and they're ending up at a lower point. Distance is decreasing. But the speed, this one's a constant speed for the same reason as before. It's a straight line, unchanged slope. For the last one, number 6, distance is increasing. As time increases, that's in a way. And since it's in a way, what kind is it? Well, we're starting off steeply and we're ending up flatly. So that is slowing. That's another type of question that we can look at. Then we've got some creative ones. Draw a graph that represents the following. The value of the land first decreased at the same rate, then remained the same. So we're going to put a graph like this, which is similar to the graphs that we've been doing. I'm going to label the axis the value of the land, and then if I'm unsure about this, I can always put time and then value. It first decreased at the same rate. So it decreased, the values increased, and then the value remained the same. So you could do one of two things. You could have something like that, or since this just says it's decreasing at the same rate and then remains the same, you can actually pick a cusp and then just have a point where this is decreasing, and then this is what we call constant, like a y equals equation, like a flat line. So that's something that we can look at just for a simple graph of this example. I know it looks like a lot of space, but not a lot of work. It's kind of what these are. Mary walked at a steady pace toward the tree. Well, if we look at the graph that we did up above, we had distance and time. So here's Mary, represented by time and distance. Now, depending on how you define this, there could be a number of examples. You could say distance from the tree. So the distance from the tree is decreasing at a constant rate until, bam, she hits the tree. That's one possibility. Now, I could show that maybe with another way. Maybe it was a slower walk toward the tree. Maybe she wasn't running to the tree. Maybe it was something like this. That was just a little bit more gradual. Maybe Mary was full-on dead sprinting to the tree, which could create a little bit of a funny thing because you could show something like that, where she actually was sprinting to the tree, bam, she hit the tree, backed off a little bit, and then blah, blah, blah. So those are all different examples of this. Chris stood at a distance from the statue. This is a boring example because as time passes and the distance from the statue, that's kind of like the distance is not changing at all as time passes. So it's a flat line. Chris's distance from the statue is not changing as time passes. You have an example. Sally walked quickly toward the roller coaster and then slowly walked away from it. So she's running to the roller coaster. As time passes, Sally's excited. Here's the distance from the roller coaster. And so she's walking quickly. Maybe she's getting closer to the roller coaster. Quickly. And then up. Just kidding. Now I'm going to start walking slowly away from it. As long as we talk about this being a steep slope and this being a gradual slope. then this makes sense. Let's fix the writing on that. Okay, there's a little bit of a delay when I write, when I'm not recording, so it's not pretty. Okay, lastly, we have Joel skiing down a Black Diamond Mountain in Colorado. This we could have some fun with, and that's where I want you to be a little bit creative. So I draw this, strange colors. Who says that ski slope is constant? It doesn't have to be. It can be any number of things. So if we're talking about maybe height, which is a fun one to do, this is time. Maybe the height is like kind of steep, and gradually, and then maybe he goes up a hill and then comes back down. And so you're actually just kind of drawing a contour map until the height is 0. Strictly speaking, if you're in mountains in Colorado, you aren't going down to 0, but you get the idea. So that could be anything that you might want to draw. So, all right, that's it.